who is Ramses Gonzalez. So Ramses is currently a doctoral student at the University of North Carolina at Chapel Hill, and he was awarded an NC Space Grant Graduate Research Fellowship for 2021-2022. And his research is aiming to identify ultra-cool dwarf superflares in the Evryscope database. So Ramses, the floor is yours.
Thank you. All right then. Good afternoon, everyone. My name is Ramses Gonzalez. I am a graduate student here at the University of North Carolina. And today I will be presenting to you my research of my searching for superflares and ultracool dwarfs using the Evryscopes. So first of all, what are ultracool dwarfs? Well, ultracool dwarfs are very small and very cold stars. As you can see from this picture, they're at the smaller end of the size spectrum, more comparable in size to a planet like Jupiter than our own sun. But why do we care about these stars in the first place? Well, these stars can host a large number of terrestrial planets. The best example of this is the TRAPPIST-1 system, which is known to host 7 terrestrial planets, three of which are within the star's Goldilocks zone. So now that we know that these stars can have terrestrial planets, the next thing we want to look at is their stellar activity. And we do this by analyzing the flares that these stars produce. Now, a flare, very basically, is an intense release of electromagnetic radiation from one of these stars. When the energy of these flares exceed 10 to the 33 ergs, we classify this flare as a superflare. For reference, the largest solar flare on record from our own sun is the Carrington event of 1859. And this flare had an energy of 10 to the 32 ergs, just shy of that superflare classification. So the thing is that ultracool dwarfs can produce flares with 10 to 1,000 times more energy. Now, this is very important because in an ultracool dwarf solar system, the planets are much, much closer into their host star. Here is an example of what the TRAPPIST-1 system looks like. And here it is in relation to our own solar system. So as you can see, the planets are much, much closer into their host star. This is critical because that means that if the star ejects a flare, those planets are much more likely to receive a direct hit from that flare. So that's very important for us to understand and to know how frequently these flares happen. The way that we detect these flares is with the Evryscopes. The Evryscopes are a pair of 2 telescopes. One is in Chile in the Southern Hemisphere, and the other one is Mount Laguna in California. They're composed of 20 to 24 individual cameras each, and they have a combined field of view of over 16,000 square degrees. They observe the sky at 120 second cadence. Now, with these telescopes, we have a massive amount of data, and the way that we automate how we look at this data is with the Evryscope fast Transient engine. This is our data pipeline that helps us analyze the Evryscope images by taking an image and then comparing it to a reference image. By looking at the difference between these 2 images, we can more easily see any transient events. In this example right here, you can see at the bottom part of this picture, you can have a little satellite trail on the left side of the difference image, and then a little tiny circle right below that, which is a variable star. And on the far right side of this picture, you have a flare from an M dwarf star. So this is how FD works. And what I did is I entered or input the coordinates for all of the known ultracool dwarfs into the FD pipeline. And what it returned is a long list of possible flare transients. Now, as you can see from this small sample of all the results, a lot of these candidates are not real transients. There are a couple of cosmic rays scattered here and there, and you occasionally see the satellite streaks in a couple of images. But every so often, you do get a very good flare candidate, as you can see here. Now, from my search, I have found a total of 11 strong candidates for superflares from multiple dwarfs, the brightest of which are these 2 highlighted in red. The first one is for an L2 type star, in which the star got 4.5 million times brighter. And this one is for a star that is approximately 200 light years away from us. The next one is for a star that got 300,000 times brighter. and is approximately about 100 light years away from us. It's for a slightly cooler star as well in comparison to the one right before this. So now that we know that we can detect these superflares, the next step is to find out how common these superflares occur. And based on that, what impact they could have on any planets nearby. And if those planets could be potential habitable planets, what impact would it have on life there, either existing or future life that could be on that planet? So with all that said, I want to thank everyone for being here. I'm happy to take any questions that you all have.
Okay, I see there's one question we'll save toward the end. Oh, there's one. Let's see. Did you have to do your research on specific equipment, or was it work you could do remotely?
So the two telescopes, the one in Chile and the one in California, they are located there. We don't have to be, they're remotely accessible. So I can just, the way that the telescopes work is they stream all their data to a server, and then I can access that server directly. So that's how I get the images from each one of these telescopes. And then the FD data reduction pipeline is also built into those servers. So it's just a lot of coding in that from remote access to that server, if that answers the question.
Yep, great. Well, thank you, Ramses. Another great talk.